So we have normal distribution. So normal distribution is most common distribution, and later you will see this is by the benefit of so-called the central limit theorem, which said if you have a large sample size and following certain property, then what you end up with is normal distribution. So that's why it's most common. That's why the name called normal. And in fact, it's in the old days it's called Gaussian distribution, invented by Gauss. It is well known. We call the bell-shaped curve. So if you know bell-shaped curve, then you know it's going to have a support from negative infinity to positive infinity. So it's basically any number in the number line. So the probability density function is rather complicated. You can see this have to be characterized by two different parameter, mu and sigma square. And mu appear once, sigma appear twice, and you have pi, you have e. So it's rather complicated, rather clumsy distribution. But if you look at the next slide, you will see this is a bell-shaped curve, so nothing very worry about. The mu just like shift around the bell shape left and right, and the sigma make it the peak is higher and lower. It's a bell shape. It's make the peak higher, lower, more flatter. Okay. And the distribution function is look like this. We have integral remain. The reason why we didn't write anything further because there's no way to simplify this. It's by technical term, it's not integratable. So basically, it's you have to use a calculator or software packages to calculate this. Regardless of this, even though complicated, interestingly, the mean and the variance is given by its two parameter. Okay, this mean is mu and variance is sigma square. Okay, so still there's some hope we can do some analysis based on this bell-shaped curve. So first, let's look at the graph. So first look at the green one. The green one is the most common one you expect is the mean 0 and sigma is 1. Actually, later you see this so-called standardized normal or standard normal. And this is symmetric about the mean at 0, right? And it's nicely symmetric, right? So later we'll use this property. And the blue one shows if you reduce the mean and increase is you receive it, right? And then you increase the decreases variance, it becomes flatter. So increases variance, it becomes flatter. And further you increase its variance, it becomes even flatter. Okay, so that is the idea behind these graphs. So for transformation, as we see, this normal is characterized by mu and sigma square. Okay, then do we need, because we cannot calculate things, so do we need a graph or table for every mu and sigma square? The answer is no, because as we have said, the standardized normal, okay, which is U minus its mean and over its standard deviation is equal to normal CO1. Okay, so this normal CO1, we can find a table, we call it Z table, will provide us that Z less than Z, okay, for only positive will be done. The reason why is because Z is symmetric about 0, so that's why next the negative, okay, can be given by 1 minus of this, okay, or 1 minus you can find from the Z table. Okay, let's see the for example. So suppose Z follow standard normal distribution using Z table, we can easily find, because from table C less than 1.4 come from table directly. Okay, this one can be come from table directly, and this one Z less than negative 1.6, okay, will be equal to 1 minus Z less than 1.6 because it's symmetric, right? So using complement rule, this will be the property. Okay, and that's 1 minus 0.9452, which is come from the Z table, then give you the answer. Okay, another way people would ask is between some range. Okay, in that case you can divide to two parts, right? You can less than 1.4 and minus less than 1.6. Okay, and this comes from the z table again, will give you the answer. Okay, another example is we have not standard normal but a normal. Okay, follow normal distribution with mu 20 and sigma square 16. So how should we proceed? Okay, we transform x, okay, standardize it, minus its mean over its SD, which is 4. So that this give us the z, this give it 1. So we can easily look at the table. Bigger than 1, right? Is the complement is less than 1, so it's 1 minus this. Okay. Whether you have equal sign doesn't really matter because it's a continuous distribution. So that's why the same thing here. And here we have x is between 16 or 24. So again, the same concept apply. We standardize it, minus 20 divided by 4. So this becomes z, this becomes negative 1, 1. The same idea would apply. This is p less than 1. This is c less than negative 1. You need to subtract it from 1. That gives you the solution. So now we want to show you the proof that when you subtract its mean and over this SD, then actually give us what we want. So C is actually 0, 1. So Z less than Z, okay? And we define Z is X minus mu over sigma, okay? So you can do the same trick, right? We can multiply by sigma, okay? And plus mu, and they become x, okay? Same for the both sides. So that's why x is equal to mu plus z sigma, okay? And then this, right, by definition is integrate from negative infinity up to mu plus z sigma. Okay, that is how we get this step. And the next step is we try to do substitution. We call x minus mu over sigma called t, okay? That become t squared, okay? And you differentiate this t, okay? Okay, will give you the sigma is gone, okay? And when x equal to that, okay, t will be equal to z, okay? So that shows this is exactly the standard normal, right? Because this is normal, you put sigma 1, mu equals 0, give you this 1, okay? So that's why is z is normal 0, 1. Okay. Now we want to show the expectation of z. Okay, 1 to z is 0, and its variance 1. Okay. So let's do this. To expect the value of z is z times its probability density function. Okay. And you do the substitution method. Now put this inside and z is gone. Okay, have a negative side here, and you integrate over 1, so give you the same element here, and this infinity and negative up to square, so give you negative infinity, and negative infinity will give you 0, right? So 0 minus 0 then is 0. So we want to find second moment, okay, is z squared, okay? And now we need to do the trick of by part, integration by part. So you take the 2 for pi out and the dz there, so you put inside and you do the by part, you multiply it, right? And the same concept as before, this will be 0, right? 0 minus 0, and this one you get in, right? This guy is exactly the distribution function, right? You integrate, become 1, okay? So the variance of z is expressed as z squared minus this guy is 1 minus 0, that's 1. And variance of x is actually variance of mu plus sigma z, right? Okay, and the mu doesn't change, right? So it's sigma z, so it's the sigma square and variance z, so that's why it's sigma square. Okay, so that's how reprove the standard normal. Okay, thank you.